de Waal theory. The Van de Waal theory. Okay, so you've heard of Van de Waal forces of attraction, you've heard of Van de Waal himself, and you've heard of Van de Waal equation. Now today we are going to look a little bit at what Van de Waal theory is talking about. Now don't forget that this is Dr. B Science classes where we do both chemistry, physics, mathematics, and biology. And you owe me a duty to only subscribe and share this particular video. Once you share the video out, tell those you are sharing it with, both in your group platforms and to your individual students, tell them to subscribe. And once they subscribe, that is all. Subscription is free. You are not paying any kobo to subscribe. And then you also need to like, and then you leave comments. Even if there are questions, we are going to attend to those questions. Now, there is a Facebook page. There's also Dr. B Science classes. And all you need to do is to share and tell those you are sharing it with to simply follow. To follow in this page, to follow this page right on Facebook is also free. And then you can like and leave comments all through. Okay, now so today we are going to look at the Van de Waal theory. Now you heard of Van de Waal equation, and this is the Van de Waal equation where P plus AN squared over V squared multiplied by V minus NB equals to nRT. This defines the Van de Waal equation. But why do we have to talk about Van de Waal equation? Now the understanding of real gases came from Van de Waal. Okay, so as far back as about 1823. Okay, so we talk about Van de Waal equation. Now this was something that came up into the world of science with something great. New theory, new ideas, and new implementations of things that were quite difficult to understand. And this was the work of Johannes Diederik van der Waal. That is his real name. His full name is Johannes Johann. Okay, yes, Johannes, and then Diederik 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 van der Waal. Now, so Johannes Diederik van der Waal was the man who single-handedly tried to describe what real gases are. Now there is a difference between real gas and an ideal gas. Now there had existed ideal gases before real gases. Okay, let me not put it that way. There had existed the ideal gas theory before you have the real gas theory. Now the real gas theory came on board through the work of Johannes Diederik van der Waal to correct some of the anomalies that were experienced in the ideal gas theory. The ideal gas equation, we know it. The ideal gas equation is simply PV equals to nRT. This is the ideal gas equation. So the ideal gas equation had always been there. You have the ideal gas law. You know, so following all the gas laws that you have, the Boyle's law, the Charles law, the general gas equation, the Avogadro's law, and all those guys, the Zach law, all those laws were there. And then you also have the ideal gas law. Now the ideal gas law came up with an ideal gas equation, which is PV equals to nRT, where P is pressure, V is volume, N is the number of molecules of gas, R is the gas constant, universal gas constant, and T is the temperature. Now, this is the ideal gas equation. Ideal gas equation. Now, this ideal gas equation that we are seeing here defines a gas in a different way. The way ideal gas equation or ideal gas theory look at a gas is completely different from the way Van der Waal real gas theory look at a gas. Van der Waal believed that the ideal gas theory was only hypothetical in nature. Hypothetical means that it does not actually exist. It is only there as an imagination, okay, used in studying. And that is true. Because there is no gas that is actually ideal if you look at the conditions that define ideal gas. Okay, now if you it's more like saying you have an ideal wife. There is no ideal wife. So, but you can just hypothetically try to describe a woman to be ideal, but there is no woman that is actually an ideal woman. In fact, nobody, no process that is even ideal in nature, because there are still one or two things around this particular process that will create changes. So, the ideal gas theory viewed gases first as being elastic in their collision. That's one thing you must understand about ideal gas. Ideal gas theory believes that not real gas, because van der Waals is real gas. But I'm talking about ideal gas now. Why we have the van der Waals theory. Okay, so ideal gas believe that number one, collision of gases is elastic. But that is not true. That theory is not true. You cannot say that collision of gas molecules in a container is elastic. What we mean by being elastic is that there is no formation of energy, when gas molecules collide. Now you can see why the ideal gas equation, the ideal gas theory, did not really work well. It's not a practical thing. It's more like a hypothetical thing. You cannot say that when molecules of... So how do we come about the kinetic energy in gases? Because if you look at the kinetic theory of gases, there is one part of that kinetic theory of gases, its assumption that talks about kinetic energy, existence of kinetic energy among gas molecules. That is coming up because of the van der Waals theory of real gases. So the ideal gases do not believe that there is any kinetic energy that exists around gas molecules during their collision. Okay, that's number one, and that was one very big minus that prompted Johannes Diederik van der Waals to introduce his theory of real gases. Now the second thing is that the ideal gas law do not really believe that there is any form of intermolecular forces between gas molecules. So if there are no intermolecular forces between gas molecules, that means there could be no form of attraction or even repulsion in terms of gas molecules in a container. And it doesn't sound good at all to believe that there are gas molecules, there is a gas in the container, gas molecules are there, and there is no form of intermolecular forces of either attraction or repulsion. And that is another aspect of the real gas law that prompted the ideal gas law that prompted the introduction of the real gas by van der Waals. And the third is that the ideal gas law do not believe that gas molecules take up any space in a container. Remember that generally one can say that a gas takes space in a container, but it does not believe that even the molecules of the gas take some spaces by themselves, hence reducing the entire space or volume of the gas in that container. Remember that in a class that we had before, we had discussed something concerning kinetic molecular theory of gases. And when we discussed that, we brought out some assumptions. And one of the assumptions was that gas molecules are point charges, and that at every point that they exist in the container, they take up individual spaces. But this was not true for ideal gas. Now you see that these three, at least others are there, but these three cardinal assumptions of ideal gas: one, gas molecules do not take up space in a container; two, gas molecules collision is elastic, so there is no form of energy that is released in the course of collision; three, there exists no molecular attraction or molecular forces of attraction or repulsion between gas molecules. These three basic assumptions of ideal gas law brought about the van der Waals theory, which describes or which introduced to you and I the real gas law. Van der Waals believes that for all ideal gases, which are though hypothetical, there exists some element of what? Of real gas behavior. That is all about it. Remember that Van der Waals law simply states that there is existence of what? Of interaction of gas molecules between themselves and the walls of the container, such that there exists a molecular interaction or force of attraction, and also there exists a sub level of occupants of volume, occupants of space rather, of the volume of a particular container. Now, if you take a look at what Van der Waals is saying, he's saying, look, for every gas, like a real gas, there do not exist anything like what? Like ideal gas. Ideal gases are only hypothetical. They are only imagined. They are only created as a fiction. And then he is also saying that there exists what? Kinetic energy between a collision of gas molecules. Hence, there must be expectance of inelastic collision. Unlike the ideal gas that talk about elastic collision, the Van der Waals theory talks about inelastic collision. Inelastic collision simply means that there exists kinetic energy between gas molecules and the walls of their container. So energy is free, and you see that is actually true. You can calculate the kinetic energy between molecules of gases in the container. So he also believed, the Van der Waals theory also believed, that there exists what? There exists intermolecular forces of attraction or repulsion between gas molecules, unlike ideal gas equation. And that is why he believed that there is always some sort of reduction in pressure. If there is reduction in pressure in the walls, in the container where gas is, then there is a possibility of intermolecular force of attraction, because once there is pressure reduction, there is what? Attraction. And this particular modification of the ideal gas equation became very unique. He also believed that the issue that gas molecules do not take up space in a container was not true. From Van der Waals theory, it is believed that every molecule of a gas take up a space, which we define here as volume in that particular container. And that is why we have the volume exclusion. So if there is volume exclusion in the container, then it means that every molecule of a gas takes up what? Takes up a particular volume, particular space in the gas container. And that is why we have that. Now, his modification of this ideal gas equation introduced two cardinal parameters. One is the pressure reduction, A, and the second one is the volume exclusion. Okay, so for you to be able to determine the pressure, which is a consequence of the intermolecular force of attraction or repulsion, you require this part of the Van der Waals equation. And this is what you will be calculating, which is the pressure reduction. And then if you must determine the volume, okay, which is defined by volume exclusion, the correction was with the value B. So the B is what you're looking for. Ordinarily, if you are to look for the number of particles of gas molecules using the Van der Waals equation, then this particular pressure correction, which is the pressure reduction to attraction, and the volume exclusion values must be given to you. Then you'll be able to calculate this particular number of moles of number of molecules of gases in the container. So this is the Van der Waals equation, but of what relevance is the Van der Waals equation since its inception, trying to modify the ideal gas equation? Now, with all the understanding from the Van der Waals equation, the modifications of the ideal gas equation was now able to allow for what? To allow for the determination of temperature at absolute zero. It was not possible to determine temperature at absolute zero for certain gases. Even though the van der Waals theory explains exhaustively its application in both gases and liquid, especially at critical points. But with the emergence of this van der Waals theory and its equation, it was now able for one to calculate or to determine temperatures at absolute zero. Now, apart from that, it was also possible to do what? To carry out a kind of liquefaction of hydrogen and helium gases. Alright, so in fact that was the first and major attempt trying to implement the van der Waals correction of the ideal gas equation. It was the first attempt of its application was in a liquefaction of hydrogen and helium gas, before even the determination of temperature at absolute zero. So you could see that all this started coming up, and scientists begin to understand that the ideal gas equation or the ideal gas theory was not really the complete idea that was needed to understand most of these processes that are now being used following the real gas law, which is built by van der Waals theory. Okay, so you could see that the van der Waals theory is not just about Johannes Diederik van der Waals. It is about the changes that it brought into science, especially chemistry. Now you can do more of the reading about van der Waals theory on your own with the little idea that we have presented to us here. It's been nice having this class with you, and I'm grateful that we have done some work concerning the van der Waals theory as it has to do with real gases, how it modified the ideal gas theory.